I'm Brett Carr, a geologist at the Hawaiian Volcano Observatory. Active volcanoes, like Kīlauea behind me, are dynamic landscapes that are constantly changing their appearance. New vents can form, the ground can collapse forming craters, and lava flows can cover the mountain slopes. As part of our monitoring of Hawaii's volcanoes, it is crucial for HVO to measure these changes in the elevation or topography of a volcano that occur due to eruptive activity. One powerful technique we apply to measure these changes is called structure from motion photogrammetry. Structure from motion photogrammetry, or SFM, is a method that uses tens to hundreds of photographs from a digital camera taken from multiple perspectives to reconstruct the three-dimensional shape of the terrain in the photographs. This technique is based on the concept that it is possible to perceive the 3D shape of an object by viewing it from multiple locations. Our eyes and brain do this naturally. By moving around and viewing it from different perspectives, I can understand the size, shape, and location of this tripod without having to physically touch or measure it. It is from this motion that we are able to understand the structure of the object, hence the term structure from motion. The trick, until recently, has been teaching a computer to do the same thing. Software advances over the past decade have allowed for the rapid generation of topographic maps or digital elevation models from photographs. And now SFM is regularly applied by HVO and other volcano observatories around the world. Creating a new map of Kīlauea's changing topography begins with taking the photos. Airborne photos work best, so HVO geologists use a helicopter or a drone to fly over and around an active crater or lava flow and capture photographs from as many perspectives as is safely possible. The photos are then loaded into the software and processed to create the digital elevation maps. How frequently we conduct these overflights to take photos and make new maps depends on the eruption. For very large and hazardous eruptions, like in the Lower East Rift Zone in 2018, helicopter or drone flights were conducted and maps made nearly every day. For smaller and less hazardous eruptions, like those within Halema'uma'u crater over the past year, we will do a flight every week or two. During an eruption, maps need to be produced quickly to inform both HVO scientists and the public about ongoing activity. At HVO, we have focused on streamlining the SFM processing such that if there is a helicopter overflight in the morning, we can produce a map later that same day. A great benefit of SFM is that it gives us this ability to choose the frequency, extent, and resolution at which we make maps so that we can be flexible to the data demands of the eruptive activity that is occurring. There are many things we can learn from the maps produced by SFM. First, they show where the lava is and where it isn't. By comparing a new map to a previous map, we can identify what has changed during that time period and calculate useful information such as the volume of lava erupted, the eruption rate, the surface area covered by lava, and how fast a lava flow is advancing. Conducting multiple overflights, creating multiple maps, and calculating a series of these measurements allow us at HVO to better understand how an eruption is evolving over time, what are the current hazards, and when an eruption might end. Working with other scientists at HVO with expertise in earthquakes, ground deformation, and lava and gas chemistry, we can combine our data sets to learn more about the magma plumbing system and how changes inside the volcano relate to the eruptions we see on the surface. In this way, SFM photogrammetry is one of many powerful tools HVO applies to monitor and study Hawaii's active volcanoes.